Day 89 Notes, Advanced Algebra 2. Today we're moving into a new unit, Unit 6, which has to deal with functions. Now we've already used functions a little bit throughout the class. This unit is really a way for us to formalize the definition of what a unit is and how it's used in mathematics. Now before we start working with functions, let's talk about a couple definitions. And the first definition I want to look at is what's called a relation. And a relation is a method used to relate a pair of objects. And it's very similar to creating a set of ordered pairs. So for example, we could relate two words to one another. Let's say I take the word blue. That might relate to you in the sense that blue means a cool temperature, whereas the word red might relate to you in terms of a hot temperature. But in either case, if I wanted to show that blue was related to the word cool, I could organize this slightly mathematically in an ordered pair. So blue goes with cool, whereas red goes with hot. Now, we might also recognize that the word blue could be associated with or related to other words. For example, blue could represent the word water, because blue and water often goes together. And red could go with something like fire. So in either of these cases, what we have is a single word, blue, that's now related to a couple of other words. And red in this case also has been related to other words as well. Now, relations have their place in mathematics when we're talking about numeric values, not just verbal values. But our point of focus for this unit is with functions, not relations. And the difference between a function and a relation is that a function is a relation where each element of the domain, each input, as we call it, is paired with exactly one element of the range or the output. So I drew my relations with arrows earlier. We might consider the object on the left side our input and the object on the right side as our output. So if I say the word blue to you, that's input, that's given to you. I input the word blue, and the output from there is the word cool, because blue should generate the thought cool in your mind. Or blue, if I say that word out loud, could make you think of the word water. So the input blue produces an output of water. But again, in this example here, with these relations, I cannot have more than one output if I want to call this relationship a function. Let me give you a mathematical example. Let's say I start with the function y equals x plus 1. Our input, the value that we get to decide what goes into the function, what goes into the calculation, is going to be our x value. We get to choose any value for x. Let's say that I make x equal to 2. Well, if x was equal to 2, then I should add together 2 plus 1, and that means that y has to be equal to 3. Again, x was our input, 2, and y is our output, the number 3. If I put the value 2 into this function, I will always get the number 3 and nothing else. No matter when I place this 2 into this function, the output will always be 3. The 2 cannot make the number 5, it cannot make the number 10, it can't make any other number other than 3 when we're using this function. I'm going to use some more examples to further explain this idea in just a moment, but before we get to those examples, let's talk about the last two vocabulary words that I'd like to discuss today, and that's domain and range. The domain of a function is its x values. These are sometimes called the input or the independent variables. This also represents how wide a graph can get. When I move to a graph and I show a function of a graph, or a graph's function on a coordinate grid, we decide how wide the function becomes, and that represents our domain. The range, sometimes called codomain because it's affected by the domain values, the range is our y values of our coordinates. And this is what we call the output or dependent variable in a function. When we're looking at a graph, the height or how tall a graph can get is also represented by the range. Sometimes we use what's called a mapping diagram to show a function, whether it exists or not. Because we sometimes say that an input gets mapped to an output, or an independent variable gets mapped to a dependent variable. That's the direction that most functions operate. And so sometimes we draw a mapping diagram to help us decide whether or not a relationship between two sets of numbers is a function. Here are two examples of mapping diagrams that do represent functions. These are definitely functions. If we look at this case here on the left, we have the number 1 that maps to the number 52, 2 maps to the number 41, 3 maps to 87, and 4 maps to 35. Each input has exactly one output. And notice that all outputs are different in this case. Now, all of the outputs don't have to be different, as we can see in this next example. The input on the left, 12, gets mapped to the number 0, 15 maps to 0, 18 maps to 0, and 21 maps to 0. Each input has exactly one output, but in this case, all of the outputs are the same. And that's okay. By our definition from before, in order to be called a function, we must have a relationship between numbers where each element of the domain is paired with exactly one element of the range. And that's what we have here. Each element of the domain is generally listed on the left side, is paired with exactly one element of the range. And in this case, we've listed the range on our right side. So domain to range. There's always and exactly one arrow that comes from each domain, and it goes to a range value. And again, it's okay if all of those domains point to the same range value. That's not a problem. But we do have a problem if we start looking at diagrams that look like this. Here are some examples of non-functions. This set of domain values on the left for this example violates our definition of a function because the number 8 gets mapped to 2 different outputs. Remember, each input has to have exactly one output. This example in the center violates our rules as well because the number 32 maps to 4 different outputs, and that is not allowed. And you might be thinking, well, that looks just like the other example from before, but remember, this example from before had all of our domain values pointing to one range value. It wasn't one range value pointing to several, it wasn't one domain value pointing to several range values. This is a problem here. This last example is not considered a function because one of its input values does not have an output. That means it does not have exactly one output because there is no output associated with that number 52. Therefore, this is not a function. Before we move forward with the examples from our textbook, I would like to also show you another way to think of these mapping diagrams. Each domain, which is also an x value, domains generally represent our x values, is partnered with a range value or a y value. So if we're looking through these diagrams here, what you might recognize is that we could write these then as coordinate pairs or ordered pairs. And so I could write the coordinate 1, 52. I could write 2, 41. I could write 3, 87 and 4, 35. And this group of coordinates would also represent a function. In the example on the right side, we could have 12, 0, 15, 0, 18, 0, and 21, 0. And this group of coordinate pairs also represents our function. One final way that we can create or show that two groups of numbers represent a function is by putting them into a table. And for this table, I might label it this way. I can write the word input, and I'll put parentheses in that, put x inside parentheses to remind us that the input is an x value. And I can create an output, label that as a y value. Now I can create a table of data for each of my objects. I can have the number 1 and its output 52, the number 2 and its output 41, the number 3 and its output 87, and the number 4 and its output 35. And here's yet another way that I can represent a function using a different method. Let's take a look at the example from our textbook. This example is an example of the cost for a stamp to mail a letter first class. And it also represents the cost in terms of cents for each year during the last 100 years. In 1900, it cost 2 cents to mail a first class stamp or first class letter. It cost 2 cents again in 1920, 3 cents in 1940, 4 cents in 1960, 15 cents in 1980, and 33 cents in the year 2000. If we were to continue this diagram, we'd have to wait until the year 2020 to fill in the next block, because you'll notice that the years have increased by 20 cents each time. And I have 3 questions that I would like to ask based on this table of data. Number 1, is this a function? 2, what are the inputs? And 3, what are the outputs? So let's try to answer number 1 first. Is this a function? Well, to answer that, you have to ask yourself a question. Does every input have exactly one output? Now, for this case, I'm going to erase the year 2020 because that wasn't part of our original diagram. So with each of these inputs, does it have exactly one output? Well, in order to answer that question and decide whether this is a function, then we better do a better job of identifying what our inputs and outputs are. So let's go ahead and answer 2 and 3 first. Generally speaking, when we create a table, the x values go on top and the y values go on the bottom. And we said that the x values represent the input. So we would say here that the inputs are the years, and we have the years 1900, 1920, 1940, and 1960, 1980, and finally 2000. So what are the inputs? Let's say that the input are years, and those years are 1900 to 2000. That means that the output has to be our rate, and the rates that we were given were a 2-cent rate, and I'm not going to write it a second time. I'll just write it once. So the rate is 2, 3, 4, 15, and 33. And now that we have our inputs and outputs defined, we can answer the question, is this a function? And you should absolutely say that yes, this is a function. Each input has exactly one output. Now it's okay that the outputs, we have 2 of the same values in the outputs, but at least we do see that each input has exactly one output. The year 1900 didn't have more than one rate applied to it. The year 1920 had only one rate applied to it. 1940, 60, 80, and the year 2000 each had one rate associated with it. That's what makes this a function. For example number 2, we're being asked to determine whether it's a relationship between the two items or a function. Let's take a look at two of these numbers, or two of these problems. Number 1 is a person's last name and how it compares to their social security number. Is this a relation or a function? Think about it for a moment. If you think of all the last names that you might know or that might exist in the United States, does each last name apply directly to one social security number? Does each input have exactly one output value? And for that answer, I hope you would recognize no. For example, somebody with the name Smith, or I should say a family by the name of Smith, could have lots of different social security numbers. If your last name was Smith, you would have your own social security number, but your mother or your father with the same last name would have their own social security number. And that would be a problem. This mapping diagram violates our definition for a function. So no, this is not a function. This is a relation. Let me do a better job of answering that. The question was whether it's a relationship or a function. So we would definitely say here that this is a relation. Let's say you go to Foot Locker and you try to buy a pair of shoes. Let's ask this question. Does shoe size create a function with price, or is that a relation? So shoe size relation related to price, or is it a function? Well, again, let's think about what might happen if I drew a map of that. Let's say I go to the store and try to buy a size 12. Well, if I buy a size 12 in Nike Air Jordans, I'm going to pay one price. If I buy a size 12 of Chuck Taylors, I'm probably going to pay another price as well. And if I think of maybe dress shoes versus tennis shoes, I could be paying a completely different price. And again, with this mapping diagram, it violates our description for a function. We can't have several outputs connected with one input. So we can't say that this is a function. We must say that this is a relation. Let's take a look at one more example. Let's consider the height of a roller coaster and scratch that. Let me put this in the other direction. Let's say the time passed while in a roller coaster or while riding in a roller coaster, and the height in which you are while riding in that roller coaster. So the amount of time that passed compared to the height that you are in riding the roller coaster. Is this a function or a relation? Well, I happen to know that riding rides at Kings Island is a very regulated process. The rides have to be checked out frequently and make sure that they're in good operating order. And they have a very, very good idea of how high in the air or what position you will be in that track or on that track after a given amount of time. So if you're 5 seconds into the roller coaster ride, they know that you're at some height. Let's say that you're at 100 feet in the air. And they know that after 6 seconds, you're going to be at 80 feet in the air because you've begun your drop. And after 7 seconds, they know that you're going to be at 30 feet in the air because you're near the bottom of the ride. There's no way possible that after 7 seconds you could also be at 100 feet in the air. It's not possible the way the ride was designed and the way they'll let it operate. There's no way that you could be at two different heights at any given time in that ride. So because each of these inputs, each of these time values as an input always is associated with one output, the height, then we know that this model would represent a function. We'll continue our discussion tomorrow.